Yes, welcome everyone. Thank you for joining us for this community roundtable from the NEAR Simcenter. The title here is Fostering Computational Wind Simulations in Research and Practice. And I'm happy to host this for the Simcenter. So the objective for the roundtable today is to explore pathways to accelerate and expand the use of computational fluid dynamics simulations for wind engineering in both research and practice. I'll do a quick introduction, just some things for how this will work today, and then how you could engage with the Simcenter moving forward as well. And then we'll start with three presentations that I'll introduce the speakers for as we get to those. The idea of these presentations is to explore kind of different applications in the wind engineering space for computational fluid dynamics. And then, think about how we might grow our community. Then after those three presentations, I will give a quick overview of an educational module that we've developed to do large eddy simulations for wind loading predictions. And then we'll wrap up with a roundtable discussion to think about pathways for achieving our objectives. So just some household items here. So you can ask questions by clicking the Q&A button at the bottom of your screen, enter your questions, and then select send. And you can do that as the talks are happening. So you can write your questions down as they pop up in your head. You can upvote questions that you want the speakers to address. You can also choose to submit questions anonymously. In addition to using the Q&A, you can also just use the chat feature to drop comments or engage in discussion. We'll have 5-minute question periods after each talk and then also the discussion session. And during both of these, I will post questions that came up in the Q&A menu, but you're also free to raise your hand and post a question or comment verbally. Just make sure that we see your name on Zoom correctly so that we can call on you easily, and then remain on mute until you're called upon. Here are a few links to stay involved with the Simcenter. So there is a registration link to register for a Design Safe account, which you will need if you want to run simulations, for example, and try some of our tutorials. You can also join discussions on GitHub at the other link. When you go to that page, you'll see different links that you can click to get more information. And then a few upcoming events. There are other community roundtables, one on regional earthquake testbeds from the Regional Earthquake Testbeds Working Group, and then one on simulating power infrastructure for natural hazard resilience. The one that is very relevant for what we talk about today is the Simcenter workshop that will happen at the conference on wind engineering in St. Louis, May 19 to 22. Where there will be more presentations and workshops on using the WUQ tool. There is also the Simcenter Programming Bootcamp that will be online this summer. And then the nearest strategic program to accelerate researchers in computing at TAC at UC Austin. Okay, I think with that, I'm gonna give the floor to our first speaker, Professor Miguel Cid Montoya. He's currently at Clemson University since 2024. He joined Clemson after 3 years as an assistant professor at Texas A&M University. He originally got his education at the University of La Coruña in Spain, but he has spent time at a number of laboratories that are well known for wind engineering. He was at the Boundary Layer Wind Tunnel Laboratory at the University of Western Ontario. And he was also a postdoc at the Natural Hazards Modeling Lab, the NatHaz Modeling Lab from Professor Karim. His research is in wind engineering, bridge engineering, and structural optimization. And with that, I'll leave it to you, Miguel, to start your talk.
Thank you so much for the
introduction. I need to stop
introduction.
sharing, right? There we go.
Okay. Let me share again. All right, well, thank you for the introduction. So the title of this presentation is an aerodynamic database for AI-driven wind-resistant design optimization of bridges. First, I would like to mention my collaborators in this work, Omar Mures from the University of La Coruña. He's an expert on AI. Sumit Berman, Ashutosh Mishra were previous students when we were at Texas A&M University, Corpus Christi, and now they are working in the Virginia Department of Transportation and in the industry. But they spend a lot of hours working on this, and so I want to thank their contribution to this work. So this is an outline of the presentation. First, the motivation for creating this database is the wind-resistant design of bridges. We want to explore how changing the deck shape is going to affect the bridge aerodynamics. Then I'm going to start talking about why we need to carry out this kind of CFD simulation. So we move from linear to non-linear aerodynamics-based design. Then describe a little bit a previous work in which we build a surrogate model using force vibration simulations and emulating those results using a basic surrogate model. Then discuss the limitations of that approach and why we should use more rich information to enhance the predictive accuracy. And then finally describe the aerodynamic database that we are finishing and we plan to release as soon as it is completed. That should be soon, in which we will have flatter derivatives, self-excited forces time series, pressure distributions that are varying with time, and also all the flow fields extracted from the simulation. And finally, a couple of AI applications that are going to take advantage of all this data. So the first thing I would like to talk about is the motivation for this, the wind-resistant design of bridges. Here we have a very simplified sketch on how the bridges are designed in industry. First, we have a company that carry out the, let's say, structural design, where they carry out finite element analysis and so on. Then they go, if we are talking about a wind-sensitive structure, we go to a wind engineering company, where they carry out some wind tunnel tests in order to validate the performance of the cross-section and provide this data for the more advanced analysis of the wind response of the bridge. Then they gather together, they do some iterations, and finally, maybe if the bridge is an important bridge, they carry out some full bridge elastic tests. The problem with this is that if they want to iterate and they want to optimize the process, it's kind of complicated because we have two different teams. We are relying on experimental approaches, and consequently, the chances to iterate are complicated. And there is one main challenge here. What is the optimal deck shape? How we can optimize the cross section so we can reduce the cost, the use of material, and also increase the safety and resilience of the structure. So in order to ask that question, me and my collaborators have been working in developing frameworks to address this question, by taking advantage of CFD simulations. So our first framework that we published a couple of years ago was this one, in which we have on the bottom side an optimization algorithm. I don't know if you can see my mouse, but I am going to use this thing. So on the bottom, we have this optimization algorithm that is going to use an initial design, analyze the responses, and iterate with it, right? But in order to do this, first we need to develop a parameterized finite element model. So every time we change the geometry of the bridge, we see how that affects to the natural frequencies, mode shapes, and so on. We need to define the wind modeling, which is, of course, given by the location of the bridge. What are the design variables that we are going to be modifying along the design process? That may include the definition of the towers, the cable supporting system, the cross-section, and everything that we want to modify. And also, in order to see how shape modifications affect the bridge aerodynamics, we need an aerodynamic surrogate model that provides us with all the aerodynamic information we need to carry out the analysis, right? So let's say that we are going to look at the buffeting analysis. In that case, we will need flatter derivatives, admittance functions, and so on. And if we use the quasi-steady assumptions, we can just go ahead and do the optimization with an aerodynamic surrogate model that is trained with force coefficients and the slopes. But this has some limitations. For instance, here in this figure, we see the cross-section of the Great Bell Bridge, which is considered a streamlined cross-section in which the quasi-steady theory more or less behaves properly. We can see that the flatter derivatives as a function of the reduced velocity, plotted using the Polytechnic of Milan formulation, they are more or less horizontal, meaning that they are kind of not very sensitive to the effect of the frequency. However, if we move to more advanced geometry, such as the design of the Messina Bridge, we can see that even though at high reduced velocities, they asymptotically tend to the quasi-steady state. And here we can see that these lines are more or less horizontal. At low reduced velocity, we have a number of nonlinearities, right? So the quasi-steady formulation is not going to work for this range of reduced velocities. This means that adopting the quasi-steady theory has some limitations, and we need to advance the CFD simulations and emulation strategies to carry out the design of the bridge using this approach. Also, in all the aerostructural optimizations we carried out, we saw that the main trend or the main response that the design does is to increase the depth of the deck. This is because by increasing the depth, particularly when we have a deck cross-section that is a box, we increase the mechanical properties, torsional stiffness, bending stiffness, and so others. Particularly, the torsional stiffness is very positive in order to improve the elastic responses, flutter response, buffeting response. But as we increase the depth, we increase the bluffness. So for geometries that are streamlines, the quasi-steady formulation is going to work well. So we are going to have a good estimation of the response. But as we increase the depth, we move to bluff geometries where the quasi-steady theory is not going to work. So that's another reason for getting rid of the quasi-steady theory approximations. So the original aerodynamic surrogate model that we had based on force coefficient standard slope and the quasi-steady theory is this one. We have a baseline geometry. We define the design variables that we are going to modify. We define a sampling plan based on those variations. We carry out the CFD simulations where we are not moving the deck. We are carrying this static, we call it static because the deck is not moving, CFD simulations. We build the surrogate, and then we use the quasi-steady theory for estimating the flutter derivatives. By doing that, we can carry out the optimization. And if the design is streamlined, the quasi-steady theory is going to work well, and we are going to have accurate results. But if it's not, then we are going to have bad accuracy. So we have advanced this by, instead of working with only CFD simulations that are static, they are dynamic. We are doing force vibration, so we extract the dependency of the fluid structure interaction parameters with the reduced velocity. So now we are considering streamlined and bluff geometries. In our sampling plan, we have the deck shape, but also some elastic parameters such as the reduced velocity, and in a new word that we are working, the angle of attack. Our simulations, they are no longer static, they are dynamic. We are reproducing the force vibration that is typically conducted in wind tunnel tests. And by doing that, we can create an elastic emulator that does capture the nonlinearities. So if we need to carry out the design and we need to deal with bluff geometries, still, as long as the CFD simulations are accurate, we are able to reproduce the bridge response. We have applied this to the cross-section of the Sunshine Skyway Bridge as a representative geometry of a single box deck, because there is a lot of research on the literature dealing with this cross-section. The first studies were conducted at Western University, but then several universities in Italy, they carry out some numerical and experimental investigations to study the effects of some geometrical parameters, for instance, the level of roundness of the corner. So thanks to that rich literature, we can use those results for validating our CFD simulations. We use the baseline geometry, which is this one here. This is the actual geometry of the bridge. The actual geometry of the bridge has sharp corners here. We are considering the rounded configuration because it's the one that has more results on the literature. And we modify the depth by increasing and decreasing this vertical distance. So we can have a representation of a design domain where we have a strong impact on the mechanical properties, but also on the aerodynamic responses of the bridge. This is the sampling plan that we carry out. These are the geometries that we are considering. This is H, the depth, this is B, the width, and this is the reduced frequency that we are analyzing. We have a higher density of samples in the lower range of reduced velocities in order to capture nonlinearities, and then a lower density where we consider that the tendency is going to converge asymptotically to the quasi-steady state. So what we were doing in terms of the simulations is we impose a force vibration. We carry out force vibration in the 3 degree of freedom in order to extract the 18 flutter derivatives. We obtain the flow fields, we extract the pressure distributions, then we extract the force, the self-excited forces time series, and then from there we obtain the flutter derivatives. We conducted, well, before that, here is a description of the mesh. In this case, the mesh, we take care a lot of having a lot of density on the wake because this is a bluff geometry. The mesh was generated by a Python code that is fully parameterized. So every time we modify the shape, it's going to adapt and produce a new mesh. And here we have examples of one of the most streamlined geometries, the baseline geometry, and the buffer geometry we have here. And also we took care of having a smooth transition from the boundary layer to the buffer regions. With this mesh, we built several meshes, coarse, medium, and fine, considering the general distribution of cells, but also the number of elements considered along the boundary layer. We have carried out verification studies in order to ascertain the independency of the spatial discretization, but also the time discretization, both for the static simulations and the dynamic simulations, in order to see that our results are independent on the modeling schemes. We carry out a lot of validation studies. Here on the top right, we see the comparison with the experiments reported by Manini et al. 2016 that were conducted at the University of Florence. These are the flatter derivatives A2, H2, A3, H3. And here we are comparing the results with the experimental tests conducted by them, numerical simulations conducted by them using a different turbulence model, and the quasi-steady approximation, where we can see that results clearly diverge from those obtained by the quasi-steady formulation, which justifies the approach that we are using. Here in this figure at the bottom, we see a comparison of the streamlines reported by Manini 2016 with our flow fields, showing that we are basically reproducing exactly the same flow fields. And here we have the time series in which we can see that even though there are slight variations of the intensity of the vortex shedding and the frequency, the amplitude of the response and the phase is basically the same, which is the one that controls the results in terms of flatter derivatives. Well, running these simulations for all the samples in the sampling plan, all the geometries considered and the frequency, we can obtain this data set of flatter derivatives. We can see that when we have streamline geometries, the most streamline geometry is the one represented in blue. These results tend to be horizontal, frequency independent, but as we increase the level of bluffness, they are more dependent on the value of the frequency, and their convergence to the asymptotic behavior is delayed to higher reduced velocities. By using this information, we can build a surrogate model. So basically at the low reduced velocities, we have the model vibrating at low frequencies. As we increase the reduced velocity, we change the frequency, and we also modify the shape. So the simulator is supposed to reproduce all these effects during the analysis and the design process. Here we have some surfaces of the result using the Scanlan notation, using the polyimi notation, which allow us to see the horizontal convergence to the asymptotic response. And we can see that this application case, as it is a bluff geometry, it has a lot of nonlinearities. And here is where it comes the question of how we should do the interpolation between the points. The thing is, if we take a look at the flatter derivatives, there are strong changes between the points that we have obtained with the CFD simulations, right? For instance, taking a look at the blue line here, we can see that we are capturing some nonlinearities here, but we don't know exactly what is going on between this point and that point. So the ability of the surrogate model to reproduce that response is based on the sampling density, right? That means that the approximation that we use, the kind of approximation that we use, is going to condition a lot of the analysis and the design. For instance, here, this is a graph that I took from this paper, Salvatori and Borri 2007, and they were discussing the different interpolation approaches that you can use when you have this experimental data, these black points here, and what happens if you use a linear approximation, an spline interpolation, or an initial function, another kind of approximation in the time domain. And just taking a look at what happened at different reduced velocities, we can see that the value can change by 20%. And of course, that affects to the bridge response and consequently the optimum design. So the key question, or the thing that we want to address here, is what information should we use from the CFD simulations, and how deep we can go, or what kind of rich information we can use to improve our interpolation capabilities. So the basic problem we are looking at is we have the design of a bridge. We are focusing on the deck shape because that's what impacts the aeroelastic response of the bridge. We carry out a sampling plan, and for every design in the sampling plan, we carry out the force vibration CFD simulations. We extract the flow fields. From the flow fields, we extract the pressure distribution. From the pressure distributions, once we integrate those, we get the forces time series, then we extract the flatter derivatives, we obtain the bridge response. How we go from the design to the response to carry out a good design? So our first approach will be, let's build a huge surrogate in which we have as input all shape and size bridge design variables, and we get as an output the elastic response. But we will have, of course, dimensionality issues. The approach that I have been describing so far is to go from the sampling plan to the flatter derivatives, and we just build a basic surrogate model that reproduces the integrated 3D structure interaction parameters. But we can go deeper. We can take a look at the force time series, and that is going to help to improve the accuracy. So for instance, in this work that we recently published, we carry out the interpolation in the time domain. So the thing that we were interpolating were the forces time series instead of the flatter derivatives. So we do the interpolation first, and then we extract the flatter derivatives. But we can go even more deeper. We can try to reproduce or emulate the flow, and from the flow, we extract the pressure distribution, the force time series, and then the flatter derivatives. So this is the approach we use for doing the emulation of the time series, in which we use temporal fusion transformers to do that. So a temporal fusion transformer is an AI technique that was recently developed in 2021. And what we do basically is to carry out the CFD simulation, for example, obtain the time series, and train this model with a lot of time series and see if we can predict the time series of another geometry or reduced frequency that is not on the original sampling plan. We did that by using the original sampling plan and removing half of the samples, which is a very demanding thing for an AI approach that typically use a training test split of 70–80%. And we can see that the model, after training, it perfectly reproduces the flatter derivatives, even the points that are not in the sampling plan. For instance, here we can see that the ones with a square are the ones that were used during the training of the TFT, and the ones that are not with the square, for instance, this point here was predicted. Since we are doing the prediction in the time domain, the possibility of the Kriging surrogate to not reproducing these points is kind of the chances that it's not going to work are very reduced, and the emulation strategy is more robust. So the reason why I am presenting this database is because we want to get deeper and we want to look at the flow fields and use those flow fields to improve the prediction strategies. So what we have in this database is the sampling plan. We have 6 reduced velocities, 7 geometries. So here, this is the geometry that we are changing the depth. Here we have these 7 designs. And in terms of the reduced velocity, this is the vibration of oscillation. We are looking only at the pitching vibration because in order to extract the flatter derivatives, we need the 3 degrees of freedom, torsional, vertical, and horizontal. We are only adding in the database the torsional response because of the storage size. And by changing the frequency of oscillation, we change, this is alpha, this is the leading rotation of the deck. This is the data that we are collecting. So on the first, we are collecting the flatter derivatives. Then we are also collecting the forces, the time series of the forces. We are also collecting the pressure distributions along the deck, so they can be also used for training AI models. And we are also collecting the fields. Since we are talking about 7×6 simulations, the fields are going to, they have 30 terabytes. Compressed, they are about 8.7 terabytes. And this data, which is, of course, smaller, they also are in the range of 30 gigabytes, and this is basically nothing. Here we have some images of the data set. This is the force time series. When we change the geometry, well, we keep the geometry and we change the reduced frequency. This is what happened. Of course, the frequency of the alpha is changing and the behavior is changing. Here we have how it looks when we change the geometry and keep the frequency constant. So here we can see that the frequency of the oscillations is the same, but the response is changing. We can see that here we don't have vortex shedding because this is similar to the flat plate, right? So the response is controlled by the force oscillation. But as we increase the bluffness, the vortex shedding is what is kind of leading the response. If we compare this in the 2 planes, how it affects changing the reduced frequency or the geometry, we can see that these characteristics are very clear. Moving to the pressure distributions, we have the pressure distributions for all the geometries, and these are obtained as a function of time. So for each of these points, and we have 1,600 points along the perimeter, we have the time series for all of these points. So this is a very rich information that can be used for training any machine learning model. Here we have the maximum, the point where we have the maximum oscillation, which is, since we are having an amplitude of 2 degrees, is +2, and this one is -2. In this figure, we are showing the mean wind velocity, again, for the same stage, where we have the nose up +2 and the nose down -2. We can see the behavior of the streamline geometries similar to the flat plate, and as we increase the level of bluffness, the vortex is becoming more apparent. Another important feature that we can see here is the size of this bubble on the top, that we can see that the reattachment point is here very close to the edge, and it grows as we increase the level of bluffness. All these properties are kind of continuous as we change the shape. We also have the flow field of the pressures all around the domain. We have the turbulence kinetic energy, which is very good for seeing the turbulence, and all these features are very clear in this figure. And that's most of the information that we have in the database. So again, we have the flutter derivatives, force time series, pressures, and flow fields. The format of this data is as shown in this description here. We can see that we have the reduced velocity in the name, then the shape identification, the frequency of vibration, and the name of the field. So there is one file for each geometry and each pair of geometry and reduced velocity. Inside those files, we have, for the flutter derivatives, this format is going to be a CVS format. For the self-excited forces time series, we have the time and then the 3 components, drag, lift, and moment. For the pressure distribution, we have the time, the location in terms of X and Y, because it is going to follow the different points of location along the surface of the deck. And for the flow fields, we are using the same format used by OpenFOAM. So because I guess that everybody is familiar with this format, so this is the format we are going to keep, and we are sharing all the output of the obtained using the K-omega SST, the Mentor's K-omega SST turbulence model. Another important thing is that we are storing a very detailed time discretization. We are saving every time step for every 0.000225 seconds in order to have rich information in time. That is critical for training the machine learning models. So just a couple of applications very quick.
Miguel, I'm sorry to interrupt, but you're about 4 minutes over your time slot already. So
sure. Okay, no problem. So here we have a couple of applications. So the basic idea is that we are going to use this for training machine learning models, and we will present in Norway in a couple of months. So I'm going to skip this. Conclusions is that depending on the modeling strategy, we need to use different CFD simulations. The goal of this work is to share this database of flow fields, pressure distribution, and so on, so the wind engineering community can develop models and advance in the wind-resistant design of bridges. Thank you so much, and sorry for the timing.
No worries. Thank you so much, Miguel. I don't see any questions right now in the chat, but I do want to encourage everyone to post questions. I have a few, but I'm going to hold these for our discussion period at the end so we can stay on schedule until then. Okay, so with that, I'll introduce our next speaker, Dr. Gonzalo Pedro. He's a principal at RWDI, where he advises designers and architects on how to achieve optimal thermal comfort, energy consumption, and production in building design. He's a specialist in microclimate studies and has contributed to master planning, ventilation, and renewable energy projects around the world. Gonzalo has a Bachelor of Science from the Technical University of Lisbon in aerospace engineering, and then a Master of Science in Mechanical Engineering and a PhD from the University of Victoria in Canada. So please go ahead.
Thanks, Catherine. Thanks, everyone. Yeah, so today I'm going to talk a little bit about what we do at RWDI and how we're starting to think about how computational tools start to influence what we do and integrate into what we do. So a little bit on RWDI. Oops, let me go here. There we go. Obviously, I don't do this in a vacuum. I actually have a lot of people working with me. Surprisingly, there are some of the names up there of those folks. If you are not aware, we also have a product called Orbital Stack, which is something that RWDI spun off a few years ago that helps architects do these simulations, interpret it. We also have some machine learning tools built into Orbital Stack. So those teams really are working in tandem to bring a lot of this exciting stuff to the fore. If you don't know RWDI, I mean, we're a consulting firm. We're about 800 folks worldwide. I think we're best known for aerodynamic studies of super tall towers. We helped design the Burj Khalifa. But we do a lot of things, including, as Catherine said, I've been really active in the thermal comfort world, getting a little bit more into the structural cladding world these days. But we do everything from infrastructure to industry to nifty things like this thing, which is a city in the middle of the desert in Saudi Arabia, which I've worked on quite a few times. So a little bit all over the place. But why do we care about computational wind engineering? Well, for a lot of reasons. Well, one is safety. So we all know that when you look, whether you're looking at wind comfort and pedestrian level wind, or whether you're looking at structural engineering on buildings, or even bridge design, all these things, there's a safety component that we have to be aware of. The other thing is, the reality is it's cost. A lot of these things we're trying to optimize, keep the safety paramount and front of mind, but obviously our clients want to optimize in terms of cost so that they can build more efficiently. The other thing is we're engineers and we love to build cool stuff. So I mean, ultimately that drives a lot of the development that we undertake. When we're talking about, I'm going to focus a little bit on carbon reduction, because I sort of mentioned that whole idea that our clients obviously want to make their projects more efficient. They want to build more efficiently. They want to reduce waste. But the way I see it, if we flip it on its head, there's a really good opportunity. It's a win-win type of proposal with regards to carbon reduction. So if you look at something like this chart on the left-hand side, which sort of defines the different project development stages, and then the y-axis is really the carbon reduction potential. There is a point where you can actually reduce your carbon by 100%, which is actually you don't build anything. So that's great. We don't see those. Clients don't come to us and change their minds halfway through and go, oh, actually, we're not going to build anything, and they walk away. Really, what we start to see more and more of is if you go to the right of this curve, right? So if you can think about building less, so reusing existing buildings. That's great. But one of the challenges with this is if anyone's been involved in retrofits, it can have a subpar performance in operational energy. It's also expensive to do. So that's a challenge. This is really where we operate. Most of our consulting business is in this space where we really want to build clever. So that means looking at the design, looking at materials use, looking at using things like computational wind engineering rather, very early on in the design phase, and get that sweet spot for impact versus cost. And then we want to build efficiently as well. And we do a little bit of work in this space as well, but it's a bit late to bake it into design at this point. We are already into construction. And if you look at it in terms of budgets, the reality is that the construction budget, that's where you build the actual thing. That is where all your money is being sucked up. But really, when we look at an accessible budget from a design perspective, it's very early on. So it's where you're looking at concept design, schematic design, and maybe a bit into detail design. So this puts a bit of a quandary, right, for us, where we have these limited budgets, but this is actually where we want to leverage all that analysis, because that's going to have the biggest bang for the buck. So really, the cost to modify goes up over time, and the cost influence goes down as you go along the project timeline. So that's the zone of influence that we want to be in. So all our tools that we have to develop have to be for that zone of influence, or really should be focused on that zone of influence. When you look at early design, the project will evolve over time. There's a lot of competing interests, a lot of competing pressures, and we get a lot of questions from architects and clients and structural engineers. And all these things, sometimes we can answer them pretty quickly with a review, with an expert, but a lot of the times we actually have to do some analysis ourselves. And so that's where leveraging these smarter tools early on in design really helps. I'm just going to quickly go through this. I just want to sort of note that we have a very different, or we operate in a very different space to, say, a car manufacturer. If you think about a car manufacturer, they'll put about $1 billion of R&D into a single vehicle design, and they'll study that design to death. They'll put so much effort into it. Then they sell this product that's worth, I don't know, nominally $20,000 to $100,000, but they're going to sell millions of them and make billions off this single design. In construction, in architecture, engineering, construction, we're doing all this effort for a single building. Our buildings are in heterogeneous landscapes. They're all different. And we have to do it at a really low cost. So the amount of money that goes into the R&D relative to what you'd say an automotive manufacturer would put in is really quite small. So this is the challenge that we have. I won't dwell on this slide. I think it's just to note that now we have all these different tools that are at our disposal. Kind of confusing, especially for a client, but I think from an expert perspective, it's really important to leverage these things at different points in the project cycle. And each of them have advantages and disadvantages. The wind tunnel is still there. The wind tunnel is still a really important piece of equipment that we use daily to look at it, to look at projects. And I don't think it's going to go away anytime soon. But I think we are seeing more and more computational fluid dynamics and even machine learning pick up a bit of the slack, and especially on the early design side, and it's starting to push into latter design as these tools get more evolved and we have more confidence in them. I'll touch upon the two topics that I think are most relevant to this topic, which is cladding and structural. So cladding is just an analysis of the pressure forces on the building facade to really understand if these cladding elements, and they can be fins, they can be actual windows, they can be paving stones, if they're actually going to pop off in a higher wind event. The thing is that what we want to do is early on, we want to identify any key issues that have to do with the actual aerodynamics of the building. And so what we did is we actually did create a couple of tools to sort of go at it. One of them, and maybe the marquee tool, is an AI solver that is actually trained with our wind tunnel data. I think we put in about over 600 projects to train the solver. And the nice thing about it is you can sort of put in arbitrary geometry. You can put in not only for the buildings themselves, but also for the surrounds, and then simulate the pressures on the buildings for a variety of directions. So this really allows cladding engineers to go in and identify hotspots, identify potential challenges, maybe modify the aerodynamics of the building, but ultimately gives them really a heads up as they are entering and completing the project that they could have these challenges down the line. Just a little bit on our actual cladding estimator. Again, we used wind tunnel projects, and it gives us directional pressure, which we then can combine with climate data to get sort of a bit more of quantitative analysis of the pressures on the building facade. So this is a quick shot of, everyone knows the Kirk building. It's a well-known model. This is an example of we tested the machine learning tool against wind tunnel, and we sort of, so that the machine learning pressure for this specific tap for each wind direction, so 360 degrees of wind directions, you can kind of see how it relates to the wind tunnel. So it definitely does a great job of tracking and the same sort of general response as the wind tunnel, which is very encouraging to see. A couple of spots here and there where maybe it's not as accurate as the wind tunnel, but generally speaking, quite happy, even on the minimum pressures and maximum pressures, which are typically harder to hit than the means. So this allows us to, apply it to sort of more complex buildings, which we've tested them against quite a few more complex buildings. And the reality is that for early design, this is a really good tool because it literally runs in seconds. So for someone working through these problems, it's a great way to quickly iterate through a variety of topics or a variety of designs. So it really allows this to do some rapid fire testing. So this is a tower design that we worked on for Gensler. We were able to go through not only machine learning, but even CFD. We did take it to CFD to sort of do some quantitative analysis a little bit beyond the ML. But even CFD was allowed us to really rapidly test a variety of tower shapes. When we look at structural, pretty much the same picture starts to arise, really trying to combine these computational tools early on, and so that we don't get surprised in the tunnel, right? Or in latter stage evaluations. In this particular case, really the CFD, in particular large area simulation, is our go-to tool, even in the early stages, just because we avoid RANs just because of its limitations, especially on crosswind cases. But LDS has shown itself to be really an excellent tool to analyze these kinds of buildings. This is an example of validation we did. This is for 36 wind direction LDS CFD, again, on that Kark building. But in this case, we actually added in some resonance. So the structural properties of the building kind of made up for the Kark building. And you can kind of see that the blue is, again, the wind tunnel testing, and the red is the LES. And it really does a really good job of tracking the wind tunnel results. So pretty happy to see this. We have tested this on more complex cases, and it pretty much follows that you are able to track and do a pretty good job that the wind tunnel, as good as a job as the wind tunnel. So let's go back to the big picture to sort of close out. So, if you look at the annual global CO2 emissions, so construction industry is really a non-trivial part of that. It's something like 23% of annual global CO2 emissions. There's a big chunk in building operations. That's more the sustainability side. But we're talking about a really large chunk that we can work on. And so if you look at a building, especially even these days, whereas in the past, operational costs were very high. So operational carbon was really the dominant feature. Over the building's lifetime, the amount of carbon associated with just heating the building, operating the building was quite high relative to the embodied carbon. Nowadays, it's actually starting to flip. We've gotten really good at sustainability. So we've gotten really good at reducing the carbon footprint of the operational side of things. But now we have to start looking at the embodied carbon. And so this is where, having that analysis early on to shave and to reduce the structural stiffness and potentially structural weight of that building, reduce the amount of steel and concrete we are using in these buildings, has a very large impact. So here are some projects that we worked on. Shanghai Tower, you're looking at about 20,000 metric tons of savings that we effectuated due to just doing a structural analysis. This one did go to the tunnel, so it was optimizing the tunnel. But that's a big chunk of embodied savings. A regular high-rise tower, not as much. That's 76 stories, 307 meters tall. You're probably looking at half or a bit less than half of something like a Shanghai Tower. But then you think about a mid-rise building, definitely not a ton, that nowhere near as much as Shanghai Tower, but you just start to think about the number of buildings and the number of mid-rise buildings that exist out there. The volume is huge. So you definitely have an opportunity here to make some meaningful changes to sort of embodied carbon just by using CWE. And I just want to finish off that one of the things we talk about at RWI is really trying to maximize our handprint. So our work that we do in trying to reduce the embodied carbon that we want to maximize our handprint, minimizing our footprint. We can always do better at minimizing our footprint, but we're getting there. So, but that's really the whole goal with what we do is really try to keep the planetary health in mind as we are doing this work. And that is it for me.
Great, thank you very much. This is very interesting to see the industry perspective. We are running a little bit late, but maybe I want to take time for like 1 or 2 questions. Nothing has been, there is one here in the chat by just, okay. It says, academically, CFD of wind tunnel simulations can face challenges in acceptance compared to traditional experiments. How steeply does professional resistance increase when your firm proposes use of not just CFD, but machine learning in real projects? Yeah, and I guess you could train them on wind tunnel or CFD simulations. But...
Yeah, so you're right. I think the professional resistance is more on the engineering side. Architects love it, as long as you cover them from from a liability perspective, they don't mind. It really is, and I think you can ask Catherine a lot about this. The work that we're doing with the ASCE. The idea is to try to bring CWE more into a sort of a more formal structure where we have validated CFD following very specific guidelines that promotes confidence in CFD. And I would say that was always the big downside. You could propose CFD, but then someone would say, has it been validated? Does it work? There's always that sort of lack of confidence. I would say that's definitely getting better. And I think over the next few years, you will see a lot of changes in that regard. Machine learning is a different beast. So machine learning, for one, there's actually lots of different kinds of machine learning in AI. So you can do everything from physics-informed neural networks to regression-based machine learning. They all have their place, but it becomes really difficult to understand and sort of justify using something like regression-based, which is not physics-based. And you present something like that. How do we know that it's going to do a great job? How do we know that someone's throwing a building that it's never seen before? How well is that going to perform? So that is something that really concerns us. So I think generally speaking, machine learning great for early design. Like I think when you're putting concept design, putting it on paper, yeah, go nuts. Let's use it for that. But as you start moving down that project cycle, then I would say you start to wean yourself a little bit off machine learning for now. I don't know, 5-10 years from now, maybe the story is different, but you start to transition more into CFD, potentially even CFD that you trust, LES, that kind of thing that has been validated. And then finally, right now, the wind tunnel is the final authority for most cases, but that might change in the near future. With regards to training machine learning, we prefer to train it on wind tunnel experiments, just because of the nature of wind tunnel. It's something that's very repetitive. It's procedure driven. So generally the data is kind of clean. We understand it. CFD, the advantage that CFD has is it's very dense information. So if you think about a CFD mesh, you're looking, let's say, at 10 million cells on a problem. That's a lot of information in a single CFD run that maybe in the wind tunnel, you don't quite have that kind of density of information. So it's a little bit of a give and take. Yeah, you have to pick what you want. But if anything, if I'm going to do anything in machine learning, I would rather focus on the high quality data.
Okay, maybe if you stop sharing your screen, Eli can set his up and you can very briefly answer the question if you focus more on physics-based or regression-based approaches in machine learning.
We do, both. I think physics-based is interesting. It's up and coming. I think we still have to see more value out of it. And by value, I mean, can I do this machine learning faster and with better quality than I can with CFD? And right now, CFD has been developed over decades and it's been optimized over decades, and we understand it very well. physics-informed neural networks is kind of early days, really. So I think, and it's not about compute power. It's really about algorithmic issues. I think there's some interesting stuff potentially coming. Maybe in 5 to 10 years, we start to see a bit of a shift. But right now, I wouldn't say we're banking on physics-informed stuff.
Okay, thank you so much, Gonzalo.
Okay.
Okay, with that, we move on to Professor Elie Bouzeit. He has a degree a bachelor's degree in mechanical engineering and a master's degree in environmental and water resource engineering from the American University of Beirut, and then MS in mechanical engineering from Johns Hopkins, where he also did his PhD. He is now a professor at Princeton University, where his research focuses on the integration of theory, numerical simulations, and experimental observations to study flow in the lowest layer of the atmosphere. His work covers both fundamentals of turbulent fluid flows and various applications for wind flow in the built environment. So please go ahead, Elie.
Thank you, Catherine, for organizing this and for inviting me to give a talk. So I'm a professor at Princeton, but physically today I'm in a hotel in Boston. But nonetheless, I'm very glad to be here. So my talk today is about, again, extreme winds, stagnation zone, and ventilation solutions for urban canopy. And as I go through, you'll understand my own background, which is not wind engineering as much as it's kind of environmental engineering and boundary layer meteorology. The work I'll present today was mainly done by Jing Huang, my PhD student, and Lucia, my Stein Montalvo, my ex-postdoc. And you'll see collaborators also listed below that. So my own interest, again, is not necessarily in fluid mechanics or wind engineering at the building scale as much as it is on really trying to understand the urban environment and what modulates the urban environments. Cities are extremely important, and we have to study their fluid mechanics because 70% of the world population will live in cities by 2050. So when we talk about mitigation of climate change and adaptation to climate change, it's really an urban problem. And today already cities use a disproportionate amount of our energy and emit a disproportionate amount of our greenhouse gases. About 55% of the world population today live in city, but you see that they consume much more than 55%. So in a way, cities are where the grand challenges of the future will be overcome to trace a sustainable future, or maybe not. And we end up with maybe not the future we all hope for. So with that in mind, fluid mechanics, you can think of it in the urban context at the building scale as basically the two previous simulations focused on to some extent. So at the building scale, these are LES simulation that my previous student, she leaded at the building scale. You're interested basically, for example, in the flow divergence and the stagnation at the front of the building, the recirculation behind the building. This is side view. This is a top view. But you're also interested in other patterns. You're interested in horseshoe vortex at the street level, in the TKE production in the wake, and potentially also in, for example, when you have a hot facet or a roof, what kind of thermals and buoyant turbulence is going to emanate from that facet. You can also think of about urban fluid mechanics at the whole city scale. And this is another study that we have done, where we basically had a city that's hotter than the surroundings, which is very typical. That's what we call the urban heat island. Cities can be up to 10 degrees hotter than their surroundings. And under conditions with no wind, closer to what you see at the top figure, what you will see is a thermal circulation where basically the hot fluid will go up, and then that will create a vacuum at the surface level, and then the thermal going up will hit what we call the inversion or the top of the atmospheric boundary layer at a kilometer, and then will be diverted. And that would normally create a circulation as you see in this in the top figure. And that's very problematic because basically it will trap heat and pollutants in the city. However, with a little bit of wind, you break this recirculation bubble and you basically get more into an advection scenario where basically the wind is basically able to advect heat and pollutants away from the city, of course, to the suburbs. So the suburban people will be affected, but basically, at least in the city, you will not have this accumulation. So we basically, in this case, we were studying again circulation and flow at the city scale, and there we basically are interested in the sort of mixed convection that you get there, where you basically have both forced and buoyant or natural convection happening, the TKE that you might get, whether, for example, in this regime, aerosols from the city can form clouds and alter urban precipitation and so on. You might also, for coastal cities, you might be very interested in the complex urban land sea breezes that might emanate. However, today I'm mostly going to focus on the intermediate scale, which is basically the neighborhood scale, where you basically are not looking at the whole city or a single building, but you're looking at a cluster of buildings. And we've known now for a while that under these cases, we can kind of conceptually classify the flow or the organization and density of the building into three regimes. If the buildings are very far from each other, we get what we call the isolated roughness flow, where basically each building is almost acting or interacting with the flow as if it were on its own. So the buildings are far from each other, so the wake from the first building doesn't really affect the second building, and so this is why we call them isolated. As they start getting closer to each other, now the wake of the windward building will affect or interact with the leeward building, and there's now this interactive regime, or what we call the wake interference regime. And as they get very close to each other, we get the skimming flow, where basically the flow comes in and the buildings are so close, there's hardly any mixing. And there's a recirculation region here that would obviously trap pollutants and heat inside the canyon. And while the buildings get very tall, you can even have two recirculations regime, one with the flow and one counter recirculating zone. And again, these would trap pollutants or will reduce the ventilation of the canyon. So at the neighborhood scale, we are also sometimes interested in, for example, how the shape of the roof affects ventilation. So this is a video we made in a wind tunnel. Maider Yaguno, my ex-postdoc, made in a wind tunnel, where the video starts with a flat roofs, as you see here, you don't see a lot of ventilation, and then it moves to a basically angled roof where you see more ventilation, and then a round roof where you see also a lot of ventilation. So you might be interested in how roof shapes at the neighborhood scale affect ventilation. Another thing that's very important at the neighborhood scale that I'm going to focus on today is basically zones in the city where you might have very strong wind and very weak winds. So in this case, I'm plotting the maximum wind speed that we observe in a large eddy simulation. And you see, for example, in red, there's a very gusty zone, and in blue, as I'll explain to you in a minute, we're going to get some stagnation zone. So you're interested in basically where in the city you might have pedestrian discomfort or safety problems because of extreme wind, or environmental pollution and overheating problem because of low wind. So when we want to study this, we can put things in a wind tunnel. However, that ends up taking a little bit of time, and some of you know the challenges of wind tunnels better than me. So we tend to do more of, we tend to rely more on simulations. So when you're working on the neighborhood scale, you can do DNS or wall resolved LES, but you cannot do it at the real world Reynolds number. That would be computationally impractical. So you could say, I'm gonna simulate a lower Reynolds number flow using DNS and wall resolved LES, and assume that wherever I observe applies to a higher Reynolds number that is in fact applies in the real world for real buildings. You can alternatively do a wall modeled LES, and there you can match the Reynolds number of the real world. However, you also have the errors that obviously in LES come from the subscale modeling, and the added errors that come from the wall modeling at the interface between the building and the fluid that become a source of uncertainty. And as you decide which one you want to pursue, the main question is which error is larger, the error of not matching the Reynolds number or the error that you get from wall modeling and subscale modeling. And the answer to this question is actually not simple, because for momentum, the Reynolds number error tends to be smaller, When you go to heat transfer, for reasons I won't delve into today, the Reynolds number becomes very important because heat transfer never becomes Reynolds number independent. And you would observe there that actually maybe the wall modeling and the subgrid scale modeling error is the least of the two evils. Other challenges we get there is that we cannot resolve each building and all the features of every single building. So you need at least to do some uncertainty quantification or estimate the signal to noise ratio, which is basically what is the signal that you're trying to measure or say something about over the numerical error that you may incur. Another challenge is what is the inflow? So you're simulating a finite area. There you can do multiple things. You can do a precursor simulation with the real neighborhood that is just upstream of your or upwind of your actual neighborhood. You can do periodic simulations and not care too much about the details of the inflow or matching the inflow of the real world. But in all cases, inflow has a big impact on the results. And so depending on what you want to do, you have to think carefully about how to set up your inflow. You can basically also ask questions about how accurate my topographic maps are, what is the impact of the diurnally varying buoyancy, and so on. There's a lot of challenges I will almost skip over today, but happy to discuss them later, to basically show you some of the physical results after we thought hard and tried to do our best, the best job we can in terms of producing good quality LES. What kind of questions can we look at or can we analyze at the neighborhood scale? So in this first paper I'll go over, we are interested in wind extremes. So we want to understand what fluid dynamics indicators that you can measure in LES are well suited for characterizing stagnation and gust zones. Now, if you don't have an LES, can you just analyze the geometry and get some geometric indicators that can tell you where the gust and wind zones might be? These are what we call the geometric attributes. And the middle question actually that I skipped over is how do these wind statistics vary between different cities, which I'm not gonna delve too much into today. So let's start with the stagnation zones. So stagnation zones are regions where the maximum wind is very large. So you can run an LES and measure the maximum wind. You cannot do that in a RANS. The problem becomes if you want to study a whole city or multiple cities and multiple conditions, running an LES for each of them is very expensive. So and also the other thing you would notice here is that the Mmax is a difficult statistic to converge and to get nice smooth maps from. So one of the things we wanted to is can we get or use a different statistic that maybe is easier than Mmax to converge and we can get from RANS. So the one we basically landed on is the mean wind that you here see as M tilde, and it's defined in the next to the right hand side. It is basically just the magnitude of the mean wind vector, plus 3 times the root mean square wind, which here we basically compute as the square root of the variance of each component. And the over bar here denotes a time averaging because you cannot do spatial averaging to estimate the Reynolds mean in a spatially variable flow. So when we plotted that statistics, you see that actually it matches the pattern of Mmax very well. So what this tells us is that the statistics that you can compute from most RANs, not all RANs, but most RANs, is a very good surrogate of where the gust zones are, and in fact is much more well-behaved or smoother than the Mmax that you obtain on the right. So we were happy with this statistics. Of course, the 3 could be 2 or 4, it doesn't matter, and there's other statistics, but this one we were happy with. The other things we wanted to analyze are stagnation zones, so zones where the wind is very weak. So again, what we can do with LES is go and measure the air exchange rate. So at any point, you can measure the effective vertical exchange rate between the point and what the air above it, and that would be the vertical exchange rate that would be ventilating the neighborhood. In LES, you can compute this map, and it's on the left. But again, in RANS, you can't compute it, and actually this one misses the horizontal ventilation that you can get in complex three-dimensional canopy. So after, again, testing different statistics, the one we ended up with is the same one we used for gusts. Except that for gusts, we were looking at regions where M+3 MRMS were large. So if I go here, we were looking at the red area where this statistics is very large. For stagnation zone, you can simply do the opposite. You can look at zones where this statistic is actually very small. And what these statistics tell you, if it's very small, is that both the mean wind that can advect pollutants or heat from the location, so this M tilde is very small, and simultaneously at the same time, there is not a lot of turbulence to ventilate this location. So the location is not going to be ventilated neither by the mean wind nor by the turbulence. And so it is indeed a stagnation zone. And you observe, for example, that this stagnation zone indeed has a low exchange velocity. Here we have an exchange velocity that is low, but this is not indicated by the M+3 RMS. But actually what happens in this corridor is that the vertical exchange is very low. However, you actually get a lot of advective exchange. So this M is large. And so indeed this zone, even though it doesn't have a lot of vertical exchange, it has a lot of horizontal exchange. So the next, these are comparing the same statistics for Boston, Baltimore, Vancouver, and Oklahoma. I'm not going to spend a lot of time on this metric or on this figure, except to tell you that basically different cities with different topographies tend to form stagnation and gas zones a little bit differently. Then we were interested in, okay, so I don't want to do LES or RANS. Can I just look at the geometry, analyze the geometry, and say something about what locations might be gust or stagnation zones? This is, again, the M+3 RMS. The yellow is the 95th percentile, so anything above the yellow is a gust zone, and anything below the 5th percentile in purple are stagnation zones. And there we tried different metrics, the density, the frontal density, and planar density. But the one I was very intrigued by, which also worked very well, is the sky view factor, which is, if you look above you, it's just the fraction of the hemisphere where you can see the sky. It's typically used in thermal comfort analysis. It's not used in wind analysis. But here you see indeed that basically all three trends, the yellow and the purple, basically go up with sky view factor. So sky view factor, or how deep you are inside the canyon, has some predictive power indeed, and there's other geometric factors you can add. The reality is none of them was perfect. So it was really difficult to just predict stagnation and gust zone from the geometry, but you can have some predictive power. So what can you do about it if you find a stagnation zone? I know I'm over time. I'm going to try to wrap it up quickly. So typically in Mediterranean streets, for example, they use shade fabric to shade pedestrians from extreme heat. What we were interested in is a solution that mixes both shading and ventilation. So in this case, we're going to use kirigami, which is the Japanese art of cutting papers. So if you have fabric that you cut in a certain pattern and then you pull it, it's going to open up in this pattern that you can see here as a mesh. And this one can offer you some shading and also can maybe improve ventilation. So the question is, how can it improve ventilation? So we're going to do some fluent simulations. And again, in this case, I'm showing you, for example, if you just try to simulate louvers, with 0 louvers, it's basically just an open street without anything on top. And if you have 2 louvers or 3 louvers or 5 louvers, you see that the air exchange rate compared to the no louver or nothing at the top increases significantly. So indeed, with simple louvers, not kirigami yet, you can actually improve the ventilation of a street canyon. And here I'm just showing also that PIV results and LES are not too far from each other. And then what you can do with this is to say, okay, instead of the louvers, if I use kirigami, what would be the ventilation? And indeed, the kirigami works as well as the louvers. You see that the kirigami at the same effective number of louvers falls on the line of the louvers, so it's almost as effective. And finally, you can try to basically scale the ventilation that you get. I'm going to skip through this quickly. The nice thing about this project is it can be built in the real world. And indeed, Lucia, the postdoc who did this, is building or has built a real world model of this that's going to be displayed in the Venice Biennale. So if you happen to be in Venice, let me know, and I'm happy to send you the details of where you can go see this starting in June. So to summarize, urban fluid mechanics, a term that was coined by Joe Fernando from Notre Dame now, are very important and exciting. You can look at them at the building, neighborhood, or city scale, and each comes with its own challenges. At the neighborhood scale, something that we've been very interested in is stagnation and gust zones, and identifying them based simply on topological metrics. And at the same time, we need to think of solutions that enhance shading and ventilations for cities. And with that, I'll just end up with a thank you for the students and postdoc who did a lot of the real work for this. More information is available at the link. And also a thank you for the Army Research Office and NSF, federal agencies that have been funding this work. And without them, this work would not be possible. And unfortunately, today going forward, that model of federal funding is kind of really being challenged, but hopefully it will survive for the sake of science. Thank you.
Yeah, thank you so much for a really interesting presentation, Ellie. Are there any questions from the audience? We can take like one or two quickly now, or come back to questions later.
Oops, maybe I should have done that, but let's try again.
I don't see any questions coming in, and I have one, but it's kind of something that I think came back for most of the presentation, so I prefer to do that maybe at the end. So maybe I'll just quickly, and I can, because we're running a little bit late, but I can be very quick on the educational module side. Just need to find the right screen share. Okay, here we go. Oh, my screen sharing is paused, it says, so I'm guessing.
Sorry, maybe I didn't, did I add share? Yeah.
I think I had the power to undo that. So do you see my screen now? Okay, good. So I'll try to do this in 5 minutes. So we have 10 minutes for more questions and discussion. But we quickly wanted to introduce this. We've been working on this for a while, and it really is almost finished now and will be published online in the next week or two. So we've developed this educational module for large eddy simulations for wind loading predictions. I took care of developing some lecture materials, so slides, and then there will be recordings of those lectures as well, while Abi, a postdoctoral researcher at the Simcenter, took care of tutorials and also an assignment that comes with this educational module. So the learning goals of the module are that students will be able to list model choices that affect the results of a wind load analysis using large eddy simulations, that they can use that knowledge to assess the quality of an LES prediction for wind loading, and that they can run and post-process an LES calculation for wind load assessment themselves. And throughout the lectures, we really try to combine practical knowledge with a relatively thorough theoretical background, so that we can really make sure that people who have taken this class understand what it means to do a quality assured wind loading prediction using large eddy simulations. So the way this is built up is really following kind of the steps that you have in setting up a computational model for wind loading prediction. So we start by defining the desired simulation output, which could be peak loads on a cladding panel, but it could also be just overall shear forces or moments, right? And then the system of interest, is it a single building? Are you reproducing a wind tunnel test? Or do you want to reproduce a more realistic configuration of a building in an urban environment? I'm thinking about the physical processes that play a role. When we think about wind loading, most of the time that is really just turbulence, and we think about neutral conditions, right? And then the geometrical characterization of the problem. Then in step 2, you have to formulate a mathematical model. So you have to define your governing equations. So we briefly cover the Navier-Stokes equations. but then also the subgrid models and the wall models that you need because of the filtering operation and because of the limitations in terms of near wall mesh resolution. And then we introduced the boundary conditions as well, with a special emphasis on the inlet boundary conditions because the modeling of the wind is very important in this setup. Okay, once you have your mathematical model in the continuous sense, right, as a system of PDEs, you have to go discretize it and then solve the system. So we talk about creating a computational grid, the discretization of the equations, and then solving the discretized system and what is important in these steps. And then in the last one, we talk about analysis of the results and about quality assurance. So in each of these steps, right, you have simplifications and assumptions that can affect predictive accuracy, and we really try to emphasize those to then get to that idea that people will be able to do a quality assured simulation. The lectures, the overview really follows that outline that I just gave you. So we do an introduction to LES for wind loading to think about the flow physics and quantities of interest. Then we introduce the governing equations, including subgrid models, wall models, and boundary conditions. We talk about how you go from these equations to a numerical solution. And then we talk about analysis of the simulation data. And then lastly, there is the introduction to tutorials and assignments. We have 2 tutorials. One is modeling ABL flows using LES. So there you work through setting up a large eddy simulation that will produce a target wind flow at the building location. And in the second tutorial, you actually calculate the wind loads on a building in that target wind flow. And then the related assignment is for students to look at grid sensitivity of high-rise building wind load calculation. And that is really to reinforce that importance of grid resolution in the simulations. The module will be available online, and this is kind of a snapshot of part of what the web page will look like. So we're targeting graduate level classes here. The learning objectives I went through before. The tutorials and the assignment use the WeUQ tool, and then we will make the slides available so people can borrow from the slides, use them in their classes, teach them themselves. We will also make the lectures available so you can the videos available so you can just make students watch the videos. And then all the tutorial materials, videos, and assignments will also be available for download. I tried 2 things before we kind of finalized this. The first one was at an undergraduate level in one of our sustainable architecture and engineering design studios. Here we tested the lectures only, not the WeUQ tutorials, because they weren't focused on wind loading. And the students were very enthusiastic about learning about wind, but when we really got to the equations, you could feel that at least half of them were kind of disconnecting from the material. However, they were very excited about being able to run simulations and doing some flow analysis. So they are really interested in learning more about these topics. Updates that I did after trying this was to integrate more visualization to try and use that to improve conceptual uptake of the information. And then moving forward, but not right now, I might explore an undergraduate specific version of this module. But for now, we really on the website are going to say that the module is mostly for graduate classes. So the second trial that we did was in a wind engineering graduate class taught by David Ruch at Auburn University. There we tested both the lectures and the tutorials. It was really nice to see the students being very engaged and enthusiastic, learning about computational wind engineering. The feedback from the instructor was very positive. He said that the module removes significant barriers to teaching students the basics of computational wind engineering and also really get their hands-on simulations and run simulations. And then we completed a course evaluation with a sample size of 6 students, but I won't really go through those results in the interest of time. I think in general, they said that they learned a lot. When we focused on specific learning goals, it indicated some things that we can improve. I think just in the delivery of the material and for the tutorials in terms of easing and streamlining some of the work there. And that's what we're working on right now before we will publish everything online. So if you're interested in this, please reach out to us and we'll definitely let you know when things are available online, and there will be more communication from the Simcenter about that as well. Okay, so I will end that presentation here. And thank you, Matt, for putting the link in the chat. And I want to open it up for more questions to our speakers. You can, of course, also ask me questions about the educational module. I don't see any new questions in the Q&A or the chat for now. So one thing I'm going to do.
Catherine, I had a question for you, but I can't find how to raise my hand.
Okay, go for it. One thing I'm going to do first is I created a super short survey that anyone who is interested could maybe briefly look at. It's like a Google form. So that we can get some feedback from you on what you think the barriers are for expanding use of CWE. But while people follow that link and try to fill it out, Ellie, go ahead and ask your question.
So you said you were considering a version for the undergrad. So I guess my two questions are, what would it take to make it like accessible to an undergrad? And if you had a senior who was motivated and wanted to do a final, a senior thesis or a final course project, would it be accessible to an undergrad, if they had enough time to spend to learn it?
I think so. So the setup of the educational module, the way I delivered this was 3 50-minute lectures, right? So it's relatively short and condensed, but I think the concepts can really be brought across to an undergraduate student who has done undergraduate fluid mechanics and who understands statistics calculation, right? I think the trial that we did was especially interesting because it's architecture students who have not taken fluid mechanics classes in general, right? So you really start from, a much more limited background. We're gonna try something next year where we actually have like an introductory course that doesn't only cover fluid mechanics, but that covers energy and structures and kind of an introduction to understanding buildings. And then I want to repeat it with students who have taken that class and see how much that helps. Because it could be that just some basic additional introduction, really helps a lot. I mean, and despite everything I said now, the students really enjoyed it. Like, even though they probably don't remember much from the equations that I taught them, right? I do think they learned a lot. So, yeah.
Thanks.
Are there other questions? So if there is no other questions, I have a question for kind of all three speakers briefly. And I think each of you kind of alluded to that and kind of, have similar challenge, right? Which is that we are dealing with a significant variety in our heterogeneity, right? In geometries that we look at. Like the urban areas have different densities, different morphologies, different characteristics. I mean, bridge deck shapes is a little easier maybe to parameterize. But as we try to give design guidelines or develop AI models, do you have any thoughts on how to deal with that heterogeneity? Do we just need to build bigger and bigger databases? Or have you in your research discovered some trends that you think we could build on, or in practice, if Gonzalo is online to answer this question as well?
I think it's a very interesting question, that one, because, for instance, for bridges, you can just parameterize with a couple of, or in any topic, a couple of points that you move, right? One of the things that we are exploring is using SDFs, signal distance functions. So by using that, you can kind of play better with the geometry. Another approach that we used time ago was a radial basis. So you define a couple of geometries and you combine them. So there are a couple of trigonometrical tricks that you can do, but at the end, I guess, the more you want to explore, the more data you need, right? So I don't think there will be a magic solution that will solve the problem, but
yeah, no, I agree. And we have found the same thing with the distance functions, I think, so that there are some powerful tools there. Ellie, did you want to add something?
I mean, we haven't used we've been using machine learning and AI in general for urban heat island and other problems, and that has been working quite well. For fluid mechanics, I still haven't had the courage to go there because, as you all know, it's really complicated. But I have, for example, I think for wall models and subgrid scale models, it can be a great tool there where the setup is simpler. I think the question is, to me, is for example, to what extent, if we train a machine learning model on square building, can it deal with slightly non-square or round buildings? Problems and geometries that change the separation point really drastically change the flow and the drag, as probably you all know. And so the sensitivity, even in LES, for example, wall models around over cubes is really wall modeling in LES over cube is much simpler than wall modeling in LES over cylindrical buildings or some other buildings where the geometry doesn't set the. So this is, I think, one of the big questions for AI techniques. I think probably AI will soon be able to predict the average load on building. It will be able to predict average loads on buildings or kind of an average drag coefficient before it is able to really predict maybe the point-wise drag or the real distribution. When you average over a building, I think there's a little bit of some averaging of and cancellation of the error that will happen. So yeah, I think it's a tool that has so much promise, so we have to try it. But it is yeah. So the one thing I would say, Catherine, going back to what you were mentioning, is that right now we have a bit of a fragmentation in the databases. So I run simulations, and then they're stored in my own format, and then you run yours, and everybody runs theirs, which is really and nobody on their own can produce the databases of the scale that is needed for machine learning. So is there a way of and again, when you train a machine learning model, some data points are bad, are lesser quality than others. So if somehow we can compile all the LES simulations, some may be better than others, into a database that is usable by machine learning, that would be great. I know recently Nagin Nazarian from the University of New South Wales in Sydney has, put one of the databases that had 100 simulations, online. But again, the problem is we share our data, but each has a different format. And so what can we do about it?
Yeah, I think that's a very good point. Yeah, I think when Gonzalo, he's online, I don't know if you can talk, but I think the power that you have is that you have years and years of wind tunnel data that is consistent and that you created and generated, right? And then you can really start training models.
Yeah, and that's certainly what we're doing.
Yeah.
I won't underestimate the amount of time it's taking us to clean that data, even from a place that is relatively organized. The reality is that 10, 20 years ago, there was no thought about doing this, right? So there's a whole bunch of broken links and all that kind of thing that we have to contend with. But I would say, I mean, to your question, I think going to the heterogeneity of the problem space, and that is that maybe we're just being a little bit too hard on ourselves. And the reality is that it's a little bit like trying to find a RAND's model that works for everything. The reality is that we just have to understand where our limitations are and what do we use for the right moment and the right point in the project. We can all do really good LES. Like, we know how to do it. This is not a question. But the problem is that it just becomes intractable and no one's going to pay for it. On the other end of the spectrum, we can do ML, and we've done ML, and we've tested it on, like, for example, the cladding. And what we found is that, yes, more data does help, that's for sure. But you do get a point where You just have to understand where there's a limitation. So for example, we first trained it on a bunch of bluff body buildings, right? That was our main data set. Now, can you apply that, to one of the speaker's comments? Can you apply that to suddenly a stadium with a large span roof? Well, the idea is it'll give you something that maybe even looks compelling, but the reality is, do you trust it? So at the end of the day, what has to happen is the other side of the coin of spending time preparing data is you have to spend time validating. And validation is not only about knowing how well it's doing relative to a wind tunnel or an experimental data set or a really good CFD data set, but it's also about training your engineers to understand when you should apply this tool and what are the gotchas. They'll go, oh, well, when we were doing the validation, this kind of building shape on this corner, that didn't work out so well. That kind of information has to be in the system and has to be perpetuated in the organization. So it becomes a little bit of training people to understand and interpret the results that are coming out of these tools, especially in early design. And then, trying to make things better for latter design. But ultimately, let's not be too hard on ourselves. Let's just see where things are, where we're limited, where it's hard to do something, where we're not doing well. But let's keep trying, right? Keep using these tools as much as possible.
Okay. Well, I think with that, we're at time. So I think that's a good note to end on. There are a few questions that remain unanswered, but feel free to reach out to either me or any of the speakers if you have specific questions that you would still like an answer to. And I'm sure we'll be happy to engage with you. Thank you very much, everyone, for being here. Thank you so much to our 3 speakers. You really made this roundtable a success. So thank you all very much and hope to see you at a future Simcenter event.
Thanks, everyone. Thanks, Kathleen.
Thank you for having us. Thank you for organizing this.